Hello everybody, welcome into another lesson and welcome to the final lesson of Precalculus. If you've made it this far, I want to thank you for being here, and this is no small feat to come to the end of Precalculus. We have covered a lot of material in this course. After this course, my hope is that you'll be more prepared and feel more prepared to take Calculus 1, 2, and 3, and then differential equations and linear algebra and everything after that. So, the goal of Precalculus was never just to prepare you for Calc 1. That's certainly part of it, but Precalculus prepares you for everything that comes after it, including all the other calculus courses and even beyond that. It's just basically, you could think of it as a grand review of everything you've learned up until that point, plus some new stuff. But having said that, let's go on to what we're really here for today. Today we're going to talk about two topics. The first one being the angle between two planes. How do we find the angle between two planes? Well, keep in mind from yesterday's lesson, when we were talking about finding the equation of a plane, you used what was called the normal vector. We abbreviated as vector n. Well, to find the angle between two planes, you of course have to come up with their normal vectors, and then it's the cosine of theta equals the absolute value of their dot products divided by the product of their magnitudes. Now, when we were finding the equation of a plane, we had a normal vector n with components a, b, and c. And of course, you plug that into the standard form of the equation of a plane. You get a times the quantity x minus x1 plus b times the quantity y minus y1 plus c times the quantity of z minus z1 equals 0. When simplified, you got the standard form ax plus by plus cz plus d equals 0. Well, what's nice about these equations of a plane, and they're surprisingly easy to find the angle between, is that the coefficients for each of your two planes on those variables, those are your normal vectors. All you need to do are take the coefficient of the x, y, and z variables. You have your normal vectors. The d, the constant term, does not matter. It's just the coefficients of your variable terms. Now, let's picture two lines, because two planes intersect much the same way as lines. If you look in these areas, you might see acute angles. They definitely look to be acute. And these would look to be obtuse. Planes intersect the same way. All we're interested in is the smaller angle, the smallest angle between the planes. So that's why we take the absolute value of the dot product, and theta is going to be between 0 and 90 inclusive. So notice, of course, you'll end up getting positive values to the right of the equation for cosine of theta, which means that'll put you in the first quadrant. So let's go ahead and do a couple of examples of the angle between two planes. I'll rewrite the formula up top. Alright, so again, let's rewrite that formula real quick to aid you. So the cosine of theta is equal to, I don't think I need it that big, the absolute value of the dot products of your two normal vectors divided by the product of the magnitudes of those two normal vectors. Alright, so there's the formula to find the angle. Now let's get into some actual equations. Alright, so we have 3x minus 4y plus 5z equals 6. And then we have x plus y minus z equals 2. Alright, so we have the standard form of the equation of two planes. We have 3x minus 4y plus 5z equals 6, and then x plus y minus z equals 2. We want to figure out the angle of intersection between these two planes. So the first thing we need to do is come up with our two normal vectors. So the first normal vector is going to be based off of the first equation of the first plane. So we can call this normal vector n sub 1 is going to be, all we need now are the coefficients of the variables. So that would be 3, negative 4, and 5. We don't care about that 6 at all. That has no bearing on what we're going to be doing. And then our second normal vector is going to be from the second equation, the coefficients of those variables. So you would end up getting 1, 1, and negative 1, and we don't care about that too. So now we have the two normal vectors themselves. So now that we found those, why don't we start by taking the dot product of those two vectors? So we will take the dot product of n sub 1 and n sub 2. So if we take 3 times 1 plus negative 4 times 1 plus 5 times negative 1, this is going to simplify into 3 minus 4 minus 5. Well, 3 minus 4 is negative 1, minus 5 is negative 6. So we have a dot product of these two vectors being negative 6. I'm going to erase some of this work for room's sake. We need to save some room here for when we go to solve for the angle. So if you need to see how I got there, please feel free to rewind the video. Alright, so there's my dot product. Now that I found the dot product, the next thing I should do is start finding magnitude. So let's find the magnitude of my n sub 1 vector. Well, that's going to be the square root of that, let's see, 3 squared plus negative 4 squared plus 5 squared, which would turn into the square root of 9 plus 16 plus 25, which would end up turning into the square root of 50, which is 25 times 2, so you would end up getting 5 times the square root of 2 for the magnitude of your n sub 1 vector. So again, I'm going to erase some of this so I can save some room. So the magnitude of the first normal vector is 5 times the square root of 2. And then, yes, we need to find the magnitude of our second normal vector. So vector n sub 2 is going to be the square root of 1 squared plus 1 squared plus the negative 1 squared. So that's going to be the square root of 1 plus 1 plus 1, which would give you the square root of 3. So the magnitude of vector n sub 2 is the square root of 3. Alright, so we have also now found the magnitudes of our vectors. Let's go ahead and start applying the formula because we've got everything we need now. So the cosine of theta, if we apply this formula, the absolute value of the dot product, so that would be the absolute value of negative 6 all over the product of your magnitude. So that would be 5 times the square root of 2 times the square root of 3. Well, this would turn into positive 6 all over 5 times the square root of 6. So that means the cosine of theta equals 6 divided by 5 times the square root of 6. So theta itself would be equal to the inverse cosine of that 6 all over 5 times the square root of 6. And let's just take this value, we'll round to the nearest degree for that value. So yes, we're going to do this in degrees today. Alright, so first let's take 6 divided by 5 times the square root of 6. And then now let's apply the inverse cosine of that value. You get approximately a 61-degree angle. So between these two planes, they intersect at a 61-degree angle. That's the angle between the planes. And I'm going to do 2 more of these, then we'll move on to the last topic. So let's continue with this. Alright, so x minus 3y plus z equals -2. (2x plus 5z plus 3 equals 0. It's almost like they're trying to trick you with that second equation, but we have these two equations for planes. So x minus 3y plus z equals -2, 2x plus 5z plus 3 equals 0. We got the equations of the planes, we need to first find our normal vectors. Again, that's just the coefficients of the variables in each equation. We don't care about the constants. So the first normal vector will just go based off of the first equation. So coefficient on x is 1, coefficient on y is -3, coefficient on z is +1. So there's the first normal vector. The second normal vector, well, we'll go based off of the second equation. Coefficient on x is 2. Notice we don't have a y term, so that means the coefficient on y is 0. And then the coefficient on z is +5. So now we have our 2 normal vectors, 1, -3, 1, and then 2, 0, 5. Now that we got the vectors, let's take the dot product of both of those. So take the dot product of these two vectors. So we'll take 1 times 2 plus -3 times 0 plus 1 times 5, which would give you 2 plus 0 plus 5, giving you the dot product to be 7. So the dot product of these two vectors is 7. And again, I'm just going to make some space here. Alright, so we found the dot product. Next thing we need to do is find the magnitude of each vector. So the magnitude of the first normal vector, that's going to be equal to the square root of 1 squared plus that -3 squared plus 1 squared. So that'll give you the square root of 1 plus 9 plus 1, which would be the square root of 11. So the magnitude of the first normal vector is the square root of 11. What the heck? Of course, my eraser had to drop. Alright, so we found the magnitude of the first normal vector. Let's find the magnitude of the second normal vector. So let's see, that would be the square root of that 2 squared plus 0 squared plus 5 squared, which is going to turn into the square root of 4 plus 0 plus 25, which would give you the square root of 29. So the magnitude of the second normal vector is the square root of 29. Alright, so there's your two normal vector magnitudes. Now we have enough information to plug those into the formula to find the angle. So the cosine of theta equals the absolute value of our dot product, which is 7, divided by the product of your magnitude, so the square root of 11 times the square root of 29. Well, that's going to equal 7 all over whatever that product is in the denominator. We'll find out. That's 319. So that would be 7 divided by the square root of 319. So that means that theta is going to equal the inverse cosine of 7 divided by the square root of 319. And now we'll just get an approximation to the nearest degree. So let's take 7 divided by the square root of 319 and now take the inverse cosine of said value. And the angle between these two planes ends up being approximately 67 degrees. So that's what you would get, approximately a 67-degree angle between the two planes. Let's do one more. And actually, this one I've deliberately picked because I want to show you something. Alright, so let's see, we have 2x plus 4y minus 2z equals 1, negative 3x minus 6y plus 3z equals 10. Alright, so we have the equations for both of our planes. We want to figure out the angle between them. Well, let's go ahead and set up our normal vectors. So the first normal vector, again, is going to be the coefficients of our variable terms in the first equation. So you would end up getting 2, 4, and negative 2. Now let's do the second normal vector. That'll be the coefficients of the variables in your second equation. So that would be negative 3, negative 6, and positive 3. So there's your two normal vectors. Now let's proceed to find the dot product of these two vectors. So the dot product of these two vectors, so we'll take 2 times negative 3 plus 4 times negative 6 plus negative 2 times 3. So that would give you negative 6 minus 24 minus 6, which would end up giving you negative 36 for the dot product. So we found the dot product of these two vectors, that's negative 36. Now that we found the dot product, let's go on ahead here and find the magnitude of each vector. Alright, so the magnitude of the first normal vector, that's going to be the square root of 2 squared plus 4 squared plus that negative 2 squared, which would equal the square root of 4 plus 16 plus 4, which turns into the square root of 24, which is the same as the square root of 4 times the square root of 6, so you end up getting 2 times the square root of 6. So the magnitude of that first normal vector is 2 times the square root of 6. Let me write that up here. And then we'll go on to find the magnitude of the second normal vector. Alright, so the magnitude of the second normal vector is going to be equal to the square root of that negative 3 squared plus the negative 6 squared plus 3 squared. So that would equal the square root of 9 plus 36 plus 9. So that's the square root of 54, which breaks down into the square root of 9 times the square root of 6, which would equal 3 times the square root of 6. So the magnitude of the second normal vector becomes 3 times the square root of 6. All right, so there's the magnitudes of the vectors. Now, we have enough information to find the angle. So the cosine of theta equals the absolute value of our dot product, which would be negative 36, divided by the product of your two magnitudes, so 2 times the square root of 6 times 3 times the square root of 6. Well, that would equal positive 36 divided by the product of those two values. Square root of 6 times square root of 6 is 6, times 2 times 3, well, that's 36, which equals 1. So then we end up that theta equals the cosine inverse of 1. Well, good news is that 1 is part of the domain of the inverse cosine. It goes from negative 1 to 1 inclusive. What angle gives you a cosine of 1? That's going to be 0 degrees, right? Theta would equal exactly 0 degrees. So there's no angle. That means there is no angle between these two planes. What does that mean? That means these two planes are actually parallel. You have two parallel planes since there's no angle between them. So if you come up with a 0 degree angle, you could think of it as there's no angle between them, which means they're parallel. They don't intersect. So that's why I picked this one. I wanted to deliberately show you this one. Now, we've talked about finding the angle between two planes. Next, let's talk about finding the distance between a point not on the plane and the plane itself. So we're going to get into that here. First, let me draw a little diagram. I'm going to draw a diagram here. So heck, I could make this a little bit bigger, couldn't I? Yeah. I would like to illustrate this well. Alright, let me just draw some generic plane here so I can illustrate what I'm talking about. Let's see, we'll call this point P. And actually, we'll call that point Q. Alright, so we'll call that point P. Alright, so this is all going to make sense in a second here, but the idea is we want to find the distance from some point Q not in this plane to the plane itself. So how do we do that? Well, this has been a minute since we've talked about this. Remember vector projections? Vaguely. I know it's been quite a while. The distance is simply the vector projection of vector PQ onto the normal vector. That's what that is. So what is the vector projection itself? Well, that's going to then equal the absolute value of the dot product of vector PQ and that normal vector n, divided by the magnitude of your normal vector. That's exactly what that projection means. So that is the formula for finding the distance between a point not on the plane to the plane itself. It's going to be the absolute value of the dot product of a vector PQ, where P is a point on the plane, to Q, which is outside of the plane, times the normal vector leading from the plane to outside the plane itself, divided by the magnitude of that normal vector. Okay, so let's go ahead here. I'm going to rewrite this formula up top. I'm going to keep that formula handy. Because we're about to apply this. So for the first example, we are given some point Q outside of the plane at 0, 0, 0. The plane itself is 8x minus 4y plus z equals 8. So we want to find the distance between point Q at 0, 0, 0, the origin, to the plane 8x minus 4y plus z equals 8. So a couple things we need. We need a vector PQ and we need a normal vector. Let's actually focus on vector PQ first. Point P is going to be on the plane. Well, the easiest way to find a point on the plane is pick an intercept. And in this case, I'm going to highly recommend the x-intercept. So let's take the x-intercept. It'll definitely be on the plane. That means we set y and z equal to 0. So you'll get 8x equals 8, which would give you x equals 1. So the x-intercept is at 1, 0, 0. Alright, so there is your x-intercept. So now we can call that point P would be at 1, 0, 0. So now we have a point P, which is on the plane. We can go ahead and find vector PQ. So that's going to then be, alright, so 0 minus 1 is negative 1, and then the rest are zeros. So the vector PQ is negative 1, 0, 0. Now the normal vector, of course, you're just going to rip off the equation of the plane. So just the coefficients on your variables, you would end up getting 8, negative 4, and 1. Okay, so now you have just found your normal vector and a vector PQ, which goes from the plane to the point outside the plane. Now let's go ahead and apply this formula. But first we need to find the dot product of vectors PQ and N. So the dot product here is going to end up being, we'll take that negative 1 times 8. Everything else is just 0 times the other stuff, so your dot product is negative 8. And let's find the magnitude of the normal vector. Well, that's going to equal the square root of 8 squared plus negative 4 squared plus 1 squared. So that would give you the square root of 64 plus 16 plus 1. Well, that's going to end up giving you the square root of 81, which is 9. So the magnitude of that normal vector is 9. So I'm going to write that up here for room's sake. So there's the magnitude. All right, now that we found the magnitude, and we found the dot product, let's apply this to the distance formula. So the dot product would equal the absolute value of that negative 8 for the dot product divided by your magnitude of 9 for the normal vector, which would just give you a distance of 8/9 units. So the distance between point Q and the plane is 8/9 units. We'll do a couple more of these just so you can get the feel of it. Alright, so we're going to pick point Q outside of the plane to be at 3, 2, 1. The plane itself will be at x minus, let me make sure I'm reading that right, x minus y plus 2z equals 4. So we need to find the distance from point Q outside of the plane, which is at 3, 2, 1, and to the plane itself with the equation x minus y plus 2z equals 4. Well, again, we need to find a point P which is on the plane. I'm always going to recommend the x-intercept. It really doesn't matter what intercept you pick. It's just, I personally recommend the x-intercept. So, to find the x-intercept, once again, set both y and z equal to 0. You just get x equals 4, which would give you 4, 0, 0. So that means we found a point P on the plane to be 4, 0, 0. Alright, so there's our intercept. There's our point P. Now that we have a point P on the plane, we can find a vector PQ. So if I take 3 minus 4, I get negative 1. 2 minus 0 is 2. 1 minus 0 is 1. So there's my vector PQ being negative 1, 2, 1. Now my normal vector is just the coefficients of those variables for the equation of the plane. So that's going to be, normal vector will be 1, negative 1, and 2. So there's my normal vector. Now let's go ahead and take the dot product of these two values, of these two vectors. So the dot product of PQ and N is going to equal negative 1 times 1 plus 2 times negative 1 plus 1 times 2, which would become negative 1 minus 2 plus 2, which would just give you a dot product of negative 1. So we found the dot product of those two vectors to be negative 1. So let me write that up here. Now the last thing to do is find the magnitude of the normal vector. So that's going to equal the square root of 1 squared plus negative 1 squared plus 2 squared, which will give you the square root of 1 plus 1 plus 4, or simply the square root of 6. So the magnitude of your normal vector is going to be the square root of 6. Alright, now we have sufficient information to find the distance, to plug all this into the formula. The distance would equal the absolute value of the dot product of P, Q, and N, so the absolute value of -1 over the magnitude of N, which is the square root of 6, or simply 1 over the square root of 6 units. So the distance would be 1 over the square root of 6 units, a very small number. I got just one more, then we're done with the lesson. Alright. Q, which is outside of the plane, will be at the point -1, 2, 5. The plane itself is 2x plus 3y plus z equals 12. So we need to find the distance between point Q, which is outside of the plane, being -1, 2, 5, to the plane 2x plus 3y plus z equals 12. Alright, first thing I suggest we do, again, find a point P which is on the plane. So point P would be, we'll make that our x-intercept. We can call that being on the plane. So set y and z equal to 0. That would give you 2x equals 12, which would end up giving you x equals 6. So your x-intercept would be at 6, 0, 0. So now we've identified a point P on the plane being 6, 0, 0. Alright, so we have a point P. Now we need to then find a vector PQ. So vector PQ would be, we take -1 minus 6, we get -7. We take 2 minus 0, we get 2. 5 minus 0, we get 5. So vector PQ is -7, 2, 5. Alright, now let's find the normal vector. That's just based off of the equation of the plane, the coefficients of the variables. So that would be 2, 3, and 1. So we've got vector PQ, we have a normal vector. Let's take the dot product of those two vectors. So the dot product, we take -7 times 2, plus 2 times 3, plus 5 times 1. Well, that's going to give you -14 plus 6 plus 5. All right, -14 plus 6, -8 plus 5 is -3. So the dot product of those two vectors is -3. So let me write that value up here. Now, last thing, find the magnitude of your normal vector, which will be vector n. So that's going to be the square root of that 2 squared plus 3 squared plus 1 squared. Well, that'll give you the square root of 4 plus 9 plus 1, which would give you the square root of 14. So the magnitude of the normal vector is going to be the square root of 14. Alright, so now we have sufficient information to apply the formula to find the distance. So the distance is equal to the absolute value of the dot product of the two vectors, absolute value of -3 divided by the square root of 14 for the magnitude of the normal vector, or you'll simply get 3 divided by the square root of 14 units for the distance between point Q and the plane 2x plus 3y plus z equals 12. Alright, so that's it for this lesson. That's it for the entire pre-calculus course. I want to thank everyone who's been with me so far ever since the beginning, those who have joined me recently, and everyone in between. You all have been amazing, and I really hope that everything I've been putting out helps you. And if you have enjoyed this content, please consider subscribing to my channel. It's completely free, it won't cost you anything, and you'll be able to get the notifications for when I post a video. So next lesson we're going to be into Calculus 1. So before that, look for my Welcome to Calculus 1 video. I'll just give you a rundown of what to expect and the textbook I use for it and all that. So thank you again. I hope everybody has a great day. See you on the next lesson.